Base titrations, here we go. So you have an acid and a base reaction here. You're going to be doing a titration. We've talked about titrations before. We have the stuff in the that we have a titrant right here, and that is the stuff that you know about. And then the analyte is the stuff that you are analyzing. Z. This is what you're analyzing. I don't know if I can spell that right or not. Okay. So here we have a base. Our base was given here. And down here we have a standard amount of acid. So we're starting out with 25 mils down here. That acid is not going to change as far as its milliliters is concerned. The base, however, we're going to be adding more in. Okay. Remember, when you are doing these burettes, they read backwards. So the higher or the lower numbers are, the lower numbers are at the top and the higher numbers are at the bottom. That's what it is. So this is starting out at, why is the eraser not working on this? Wednesday, but it is a Thursday-ish day. So. All right, so they're telling us here that this is going to be 2.16 mils, and when we get done here, that it is 28.39. So if we subtract those values, that tells us how many mils of base we used. So we have our milliliters of base, and we have our milliliters of acid. Okay. They gave us the concentration of the base here, and we can calculate the concentration of the acid. Now, if these are both strong, acid and base, and we know them to be strong, we can use this equation to calculate the molarity of the other item. But if we don't know if it's strong or not, then we have to throw that out the window. Okay. And it looks like, they tell us here, unknown concentration. It just says the flask contains a monoprotic acid of unknown concentration. So we cannot use this. The only time that formula works for us for calculating molarity is if we're at a strong. Okay. So that's unfortunate, because otherwise this is easy. All right. Remember, you're going to have an indicator in there. Now, for your lab that you're doing, you're not actually going to have an indicator in yours. Okay. Now, how do you know when you get to the point where you're done? Well, what you're going to have for your lab is, this is actually going to be a beaker, so it's going to be wider. You're going to have a pH probe down inside there, and you're going to be just taking samples as you're putting this stuff in. And you're looking for your titration. So if we're starting with acid, it's going to start out here. You're going to have a upslope, and then it's going to go whoop, and then like that with the base. Okay. And what you're doing is you're looking for this equivalence point here and that volume. And what you're going to do is you're going to take that spot, you're going to do a second derivative of it, which you don't have to do. The computer will do for you, because I don't know how to do them, and neither do you need to, because you don't need calculus for this course. But if you're such a nerd that you want to go ahead and do that, you go right at it. Otherwise, the rest of us are just going to let the computer do it for us. Okay. All right. So we're going to talk about what that indicates and that value and stuff as we move through here. Okay. But we're going to be looking for that equivalence point, and we'll know it because we're going to see that straight up and down vertical line. Okay. So at the equivalence point, so where you are at that equivalence point, your moles of your acid will equal the moles of the base. So moles acid equal moles base. These are equal to one another at equivalence point. So if you know where the equivalence point is and you know the molarity of that base, you know the number of moles of it because you knew the volume that you used, then you can figure out what the moles of the acid are. And you already knew how much you had of the acid because it was 25 mils. That's going to give you the molarity of that acid. Okay? So titration can be constructed by plotting a pH against the volume of the titrant. And like I said, you're going to just have a probe that's going to do all of this stuff for you. It's going to track all of this for you, which is kind of cool. Okay? The shape of that curve is going to vary depending on the titrant and the analyte. So what is in here and what you're analyzing. Okay? And they're going to indicate the strengths of those acids and bases and how much they dissociate. So if we are looking at a titration of a strong acid, strong base, we know the material in the flask. So this is our flask. We're taking the pH of that flask. We're starting out with what? An acid or a base here? What's in that flask? An acid or a base? Acid, because your pH is less than 7. Okay, so the flask contains acid. All right. Now, if your equivalence point ends up being 7, that means you were working with a strong acid and a strong base. This is what you did in first year chemistry. You did a titration of a strong acid, strong base back in the day. Okay. So that titration will end up with an equivalence point at 7. At this point right here, okay, so they've taken that line, they found the middle of that straight up and down line, and that is your equivalence point. That will come in at 7. And then this is beyond the equivalence point, which is why the pH is greater than 7. All right. Again, you can use this formula if you know you're in a strong situation. But that is the only time you can use this formula to solve for molarity.
So below the equivalence point, do we have excess acid and then above it we have excess base?
Yep. And that's why your pH is coming in less than 7 here, more than 7 here, and then it's neutralized right here. Because you have excess acid here, you have excess base here. And we saw some of the calculations yesterday, how that kind of played out, right? All right. The next example here is going to be a weak acid. So this is what your lab is going to be like when you are doing the lab. You are trying to figure out the identity of the acid by calculating and determining the Ka value. And I'm going to show you how to do that. It's not bad. It's an easy thing to do with the graphing software we have. Okay. So when we are doing this, first of all, you need to get comfortable with being able to just look at these graphs and tell if you're dealing with a strong acid, strong base, weak acid, weak base. Okay. So here, I know that this is an acid, right? I've got an acid in my flask because the pH is less than 7. My equivalence point is up here at 9. Do you see that? So if I have an equivalence point greater than 7, that means that I'm dealing with a strong base as well. So this is weak, and this is going to be strong. Because I'm starting out here in the 4-ish range, and at my equivalence point is less than or is greater than 7, and I've got, base over here. I've shot past my equivalence point, and now I'm in a basic situation. Okay, So this is the general same shape as this, but it's just not as stark. Do you see how you don't have that very long extension here for the up and down? That's why it's nice for you to use that second derivative on the computers, because that'll tell you where this midpoint is. So one of the interesting things about this is when you have this situation, when you are at midway to the equivalence point. So here is your equivalence point. That is 35 milliliters. So half equivalence point would be how many milliliters? What's half of 35? 17 and a half. So if I find where 17 and a half is, I go up to the line and over. I find what that pH is. That's about 5 here. Okay. At that point, at the half equivalence point, your pH equals your pKa. So for your lab, if you can figure out where that equivalence point is, you divide that volume in half and determine what the pH is, you've got your pKa. And if you have your pKa, you also have your Ka. Right? Because if you take 10 to the negative pKa, you now have Ka. Yes?
Yes.
Okay. And this is what a lot of the tables are listed as, and then you can identify what acid you're dealing with. Kind of cool. And yeah, somebody said KB. Yeah, we could figure out KB from this as well, but I don't know that that's going to do anything for us. So now, this is what I got in trouble with a few years ago, telling kids they're only going to give you ones for this kind of problem. They're only going to give you, I was trying to say monoprotic acids, and what I said, they're going to give you ones. And they thought that they were going to get, everybody in the room was going to get ones on the exam. So they will only give you monoprotic acids for these types of problems where you have to do calculations. They may give you a graph like this where you would need to identify the fact that you have two. So this would be a diprotic or polyprotic acid because you've got two equivalence points here. That means that you're going to have two hydrogens coming off that you're going to have to equalize or neutralize, I guess would be the proper term. Okay, so this is what one of those polyprotic graphs were. Sometimes there's even ones of these where there's three of them. So like phosphoric acid, there would be three straight up and down areas here. So if you have three straight up and down areas, then that's an acid where you've got three of these, you know, or this is a -3 charge for whatever that anion is. So this guy right here, though, is a -2 because you've got oh, why does the eraser not work on here like it should? Why can't things just work? Things just can't be simple. So we would know we may not know what that anion is here, but we could derive the formula of it just from this graph. Does that make sense? Because you've got two hydrogens that are getting neutralized. All right. So next one. You are given a strong acid, strong base titration curve that's listed here. You're going to estimate the equivalence point and determine the concentration of the hydrochloric if you're given this. Now, this, we don't even need this graph for really because, well, I guess we do because we need to know the volume of the NaOH. So the volume of the NaOH at equivalence was 25 mils. So because this is a strong, we can use M1V1 equals M2V2. This is the only situation where you can use this, okay? You feel like you're cheating just a little bit because it's just too easy. The other beautiful thing about this equation is that you can keep everything in milliliters too. You don't have to convert to liters, which is kind of nice. All right, so we are determining the concentration of this. So we're solving for M1. We know that we had 20 milliliters of HCl here. Our M2 was given in the problem, which is 0.121 molar. And we're multiplying that by how much we used, which was 25 mils. So solving for M1 equals, my handy dandy calculator, 0.121 times 25 divided by 20, and I end up with 0.151 molar HCl. That was too easy. That just felt too easy, didn't it? All right. Here we have oxalic acid, okay? We know that this is a weak acid based on this graph. We know that we're starting with an acid here. Now we're going to determine if it's strong or weak. Well, I find my equivalence point. That's the straight up and down arrow. I find where the middle of that is, and I go over here. Is that value above 7? Then that means that this is a weak acid. Okay, so without even having them, tell us, or if they didn't even tell us this, they just said an acid and they didn't give us any of this stuff, we should still be able to determine that this is a weak acid just from this graph. Is that making sense? All right. So we have estimated that equivalence point here, or we've not estimated, we've determined it, okay? They wanted us to estimate the pH at equivalence. I'm going about 9 with that. And estimate the pKa of this. So half of 9, or half, this was what, how many mils? About 30. So we want to find 15. So at 15, if we could possibly draw a straight line here, which I don't know if I can or not. So there is my half equivalence point, my pH. So that looks like about 2.8. So at half equivalence, my pKa equals my it looks like they said 8.5 for this. So they were going 8.5. They're going to give you a range, though, when you take this test. So they'll give you kind of a threshold range, and it's usually fairly generous. So this is 2.5. So my pKa would be 2.5 at half equivalence. So, okay. So yeah, they'll be pretty generous with the threshold that they give you for that. So that is titrations in a nutshell, guys. There's more to it than this, and I want you to spend some time watching a video. So I'm going to give you, I want this for homework tonight, and then I'm going to give you this video that I'm going to have you do. And we may end up getting a little bit faster in this chapter than I anticipated. So I want this done by, let's say, Monday. Can you watch a video and do some stuff by Monday? Yeah. Number 2 on the you do?
Yeah.
Okay.
It's not like really the same as.
Okay, so let's look at number 2 then. Okay, so here we have our titration here. Okay, our first thing I'm going to do is I'm going to find that equivalence point. Okay, and I'm going to go over. And they want to know what we're analyzing. So the given titration, what are we analyzing? We are analyzing the stuff that is our base, it looks like. So our base is what we're at looking at, because the pH is starting out higher than 7. So that's what's going to be in our flask. Okay. So we're analyzing that. So our base here has been identified as NH3. Okay. We know that our equivalence point is coming in less than, I don't know what happened there. Our equivalence point is coming in less than 7, which means that this is a weak base. So even if they didn't tell us what it was, we should be able to figure out from this graph that this is a weak base. Yes? Okay. What's going in there then is going to be a strong acid. So that's going to be your HCl, because we're eventually going to end up with excess amount of that. So that's what's in our burette. How much do we have to get to that equivalence point? Well, I'm going to drop this line straight down, and it looks like it's, well, I went a little shady off to the side there. So I don't think it's 30. I think it's a little more than 30. Let me see if I can.
32.
Yep, I'm going to go 32. So that's 32 milliliters. If I could possibly draw a straight line here, you might be able to see that it's 32 versus, you can probably do it better on your sheet than mine. Okay. Now, on your AP exam, they do not allow you to have like rulers or anything like that, but they allow you to have extra pencils. Okay. So if you take one of your extra pencils and you lay it down, and then you take your other pencil and move it along the side of that pencil, you can get a straight edge to be able to identify some of these graphs and be able to draw a straight line down there. Okay. So even though you don't have a straight edge, they won't let you keep an ID out. They won't let you use any of that stuff for a straight edge. They let you have extra pencils. So that can become a straight edge for you. Okay. So when you're trying to drop these lines down, that becomes important. All right. Huh?
You can use your calculator too.
Yep. Your calculator cover, all of those things can be straight edges, and they'll come in handy. I mean, these are little bitty hacks, but sometimes they can, save you time and energy. All right. So if that's 32, then I need to estimate my KB value. Okay. Well, we know that our Ka is half equivalence. So half of 32 is 16. Okay. So I'm going to go over here and I'm going to try to find 16. So here's my 16. And now I'm going to try to go across here. That did not work out well. Let's try that again. It's a little harder to do this when you're, that went uphill again. So, all right. So that ended up being about 9.5. So our pKa at half equivalence is 9.5. Huh? No, this is pKa. pKa at half equivalence is 9.5. It doesn't matter. The pKa is at half equivalence. So then pKb can be calculated by doing what? Easier. What? 14 minus 9.5. Yes. 14 minus 9.5 is 4.5. And then pH at equivalence, if we wanted to do that, we would try to get a straight edge going here and go across. So about, I don't know, 5.5, 6. What's wrong? So there's my midpoint right there. Good? Does that help, Presley?
Yeah.
Okay. All right.